So in this part we're going to talk about the various factors that influence the mechanism as well as the rate of your nucleophilic substitution reaction. Okay, so the factors that actually affect the rate of the reaction depends on the energy of activation. So any factor that affects the energy of activation will have a direct effect on the rate of your nucleophilic substitution reaction. Now we have to know that this energy of activation is calculated based on several factors, for example, your bond strength, the steric factor, the heats of solution, and all these factors which are used to calculate the energy of activation are conflicting. So, whatever you get is not a quantitative approach, but a qualitative approach has been discussed for the factors because the value of E is conflicting. Okay, so here we are going to see a qualitative approach for the influence on the rate of hydrolysis of alkyl halides. Okay, so what are the factors that qualitatively influence the rate as well as the mechanism of hydrolysis of alkyl halides will be discussed further. Okay, so the factors that actually affect the rate of your nucleophilic substitution reactions are the nature of your alkyl group, and in this particular section you will be seeing two effects. One is the polar effect, wherein we'll be talking about electron donating and electron withdrawing groups and their influence on the reactivity or the rate of your reaction as well as the mechanism of the reaction. Then we'll move on to steric effects. Steric effects means whether the molecule is crowded or not. Okay, the second point that we will be seeing is the nature of your halide ion. By this time you very well know that your halide ion is the leaving group in your substrate. So based on whether the halide ion is a better leaving group or a poor leaving group, then it would directly influence the rate of your nucleophilic substitution reaction. The next one is the nature of the nucleophile. This nucleophile is the attacking reagent or the incoming group. And finally, we'll end up with the solvent effects with special mention to dielectric constant and solvation. Now, in this particular slide, we will be discussing the nature of your alkyl group, and we will be seeing the various polar effects as well as your steric effects. Now, what is inductive effect? In order to know what this polar effect means, one needs to know what inductive effect is. Okay, so inductive effect can be defined as an electronic effect which leads to the polarization of your CC bonds due to the presence of an electron withdrawing or electron donating group. It operates through space. Okay, so we'll try to understand this inductive effect by means of this particular example. What is this? This has two carbon atoms and one halogen attached to your CH2 group. So it is ethyl halide. Okay, this X means halide. Now, if I consider the nature of your halogen atom present in this molecule, then I know that halogens are electronegative in nature. What is electronegative? It means this particular atom has the tendency to attract the bonded pair of electron towards itself. As a result, when electrons are attracted towards your halide, this particular carbon which is adjacent to your, or the carbon which directly holds your halogen, becomes slightly positive in nature. Okay, when this carbon becomes slightly positive, then this methyl and this carbon-carbon bond will become polarized. Initially, when your carbon and carbon group, in the absence of your halide, in the absence of halogen, was of chargeless, okay? They both did not carry any charge. But just because of the presence of a halogen atom, the bond between carbon-carbon has become polarized. That is, this would carry a negative charge initially, and because it carries a positive charge initially because halogen is electron withdrawing in nature. And just because this carries a positive charge, this will further try to donate its electrons towards or move its electrons towards your carbon atom. As a result, this carbon gains slight positive charge, negative charge on it, and this carbon gains slight positive charge on it. Okay, so in other words, I can say initially, uh, if you just consider your ethane molecule, both these carbon are neutral, they aren't charged. But if I substitute one of the hydrogens of a methyl group with a halogen, then my carbon atom, my carbon initially bears a slight positive charge and this would bear a negative charge. Since this bears a positive charge, the electron will move towards your carbon. As a result, this becomes slightly positive and this carbon becomes slightly negative. Now I can say that my carbon-carbon bond has become polarized due to the presence of a electron withdrawing group. And this polarization of your CC bond due to the presence of either an electron withdrawing group or it can be an electron donating group, then that is called as inductive effect. Okay, so now let's see what effect it has on the rate of your either SN1 reaction or your SN2 reaction. So what one would predict is, if you have a carbon and a halogen bond, if this is the reaction center where your nucleophile actually attacks and displaces your halogen, then if this particular carbon has any group which can donate electrons to it, then this would become much more stable in nature. Okay, and you have seen in your SN1 reaction, the intermediate is a carbocation. So, if we have more number of methyl groups attached to your carbon, the center which forms the carbocation, then this would further stabilize your carbocation and increase the rate of your reaction. So, more the number of electron withdrawing groups, more it can stabilize your carbocation during your SN1 reaction, and the rate of the reaction will simultaneously increase. Okay, and the opposite is true for your SN2 reaction, because in SN2 reaction you would have seen that if there is a lot of methyl groups present, then the transition state becomes crowded. In fact, we are going to talk about that in steric factors also. But what you have to note down is, if you have primary alkyl halide, which means a carbon which is attached to either 4 hydrogen, 3 hydrogen or 2 hydrogen, then it is called as primary carbon. So if you have a primary carbon attached to an halide group, then you call it as a primary alkyl halide. So if you have a primary alkyl halide, then that would prefer your SN2 mechanism. And if you have a tertiary alkyl halide is one wherein your carbon carrying your halide group does not have any hydrogen attached to it. Okay, so if your carbon is tertiary in nature, then the reaction would proceed via SN1 reaction. Now, we are clear about what happens with primary alkyl halides as well as tertiary alkyl halide. Now we are going to see what would be the case in case of your secondary alkyl halide. So what is a secondary alkyl halide? A secondary alkyl halide is a carbon carrying one hydrogen and that carbon attached to your halogen group. Okay, so if you say this is a secondary carbon, it means this carbon should be attached to one hydrogen, just one hydrogen. Okay, then this becomes a secondary carbon. And since your halogen is directly attached to your secondary carbon, this particular molecule is called as a secondary alkyl halide. In this case, because it contains three carbon atoms, it is called as isopropyl halide. So this is the prediction based on your nature of the groups that is attached to your reacting center, and this was further proved by Hughes and Ingold experimentally. They found that when your methyl bromide, ethyl bromide, isopropyl bromide and your tertiary butyl bromide, when they were subjected to hydrolysis in alkaline aqueous ethanol at 55 degrees, they found that the hydrolysis followed second order kinetics for methyl bromide and ethyl bromide and isopropyl bromide. Okay, whereas the hydrolysis followed the SN1 mechanism in case of your tertiary butyl bromide and your isopropyl bromide. Now, considering the rates of the reaction, since this particular tertiary butyl bromide follows SN1 mechanism, then more the number of methyl groups attached, then more stable carbocation it would produce and the rate of the reaction would be greater, and that is what is seen experimentally. It has been found that tertiary butyl bromides react very quickly towards hydrolysis via SN1 mechanism, whereas your methyl bromide and your ethyl bromide, which are primary in nature, these are primary alkyl halides, they react via SN2 mechanism and the rates decreases when the number of methyl groups increase. Okay, so in this case there is only one methyl group, so the rate is around 2140 into 10 to the power 5, whereas in case of ethyl bromide it has decreased to 170. You can see there is such a vast difference just by the addition of one particular methyl group to it. Okay, and in case of isopropyl bromide, you see that the reaction is pretty slower. Okay, it is much slow when compared to your primary alkyl halides. Okay, and your tertiary alkyl halide does not react by this particular mechanism, that is, it does not react by SN2 mechanism, but it completely follows your first order kinetics, that is, it reacts via your SN1 mechanism, and that can be attributed to the presence of electron donating groups that is present on the carbon. Okay, that would stabilize your carbocation and your molecule becomes much more stable and the rate of the reaction increases. Well, Hughes Ingold, they have also shown that under a set of given conditions, so the condition should be the same, then the kinetic order for your primary alkyl bromide with ethoxide in dry ethanol also remains the same, but the rate of the reaction decreases as the number of carbon atom increase. The reaction proceeds via SN2 mechanism. So what are we going to consider? If you consider the series methyl, ethyl, N-propyl, N-butyl and N-pentyl halides, then if you carry out the hydrolysis with ethoxide in dry ethanol as the solvent, then at 55 degree the relative rate of the reaction has been given below. You see that the primary alkyl halide methyl and ethyl halide, they have quite bigger rate, but methyl halide has much it reacts in a much faster way when compared to your ethyl halide, and the relative rates is the difference in the relative rate is because of the difference in the number of carbon atoms that is attached to each of them. Okay, so in your methyl halide there is only one carbon, in ethyl halide there is two carbon, so the rate decreases. In N-propyl halide there is three carbon, the rate further decreases. In case of N-butyl and N-pentyl halide, the rates are much more less when compared to your methyl halide. So more the number of carbons, less would be the rate of the reaction when it proceeds via SN2 mechanism. They have also shown that the rate of the reaction